All right, our topic of the day is Euler's method. And you got to keep in mind when Euler was around, there were no computers, graphing calculators, no way to get technology to find these values. So he came up with this method of approximation, kind of creating a systematic process to solve for some values. And we today use these maybe more so to see the beauty of it, or maybe if you're computer programming, you can see like how these computer programs kind of set up and work. But here's kind of the idea of what might be happening. Let's say we have some graph, and on this graph, we know an initial value. Like this information we know is that we start at, I'm making up an example here at 1, 1. But let's say if I only knew that, I want to know where would I be when I'm at the value at 2? Like, am I up or am I down? What's happening at the next point? Well, the way that, the ideal way to know that would be if you had the function that we were able to plug 1 in to get that y value. And if you had the function and you could just plug in 2, then you would have the y value for 2. But this situation is pretending we can't figure out the function. We don't know what the function is. But what we can give you is here's what's given here, is I can give you the initial point. The initial point was at 1, 1. I just made up 1, 1. It's not every problem is 1, 1. But I can give you the initial. And the other thing I'm going to give you is the slope, or the dy dx. So somehow I give you the dy dx, but I don't tell you what the original function is. And finding the original function would be impossible without computers, let's say. So if I told you we started here and then I was able to tell you the slope, then you should be able to estimate where the point would be at 2. For example, let's say the slope is like this at 1, 1. You could see then maybe that would take us to about here for where 2 would be. And, let's say I plugged in and got a different slope. Like, let's say the slope was very steep here, then you could estimate that 2's value would be way up here. So it doesn't matter, but that's the idea, is like we could use that slope to estimate where that next point would be. So for example, let's just pick this, say, is the slope. So as an estimate, then we would follow and say 2's value would be right here. And then from there, we now have another point that we can use. So instead of using the initial at 2 or 1, 1, we have a new point, and then we could find the next slope. And that next slope may be even steeper, which would then allow us to get the third point, maybe get steeper, who knows. And now the third point is up here somewhere. And so we could estimate values continuing on as long as we know a point and the slope. We can keep going, and who knows, it might bring back down. But that's the idea. So here's how his method works, is that we start with an original x1 value right here and an original y1 value right here. And those values were just given to us. X1 was given to us at 1, 1, the initial, and the y value was given to us. But then our first concern was what happens at x of 2. So when we do that, to get x of 2, all we had to do is take x of 1 plus, and then decide how much we wanted to change from 1 to 2. So plus delta x. So from this point to this point would be a delta, or a change of x. And we said from 1 to 2, that would be a change of 1. To get the second y value, to figure out where that one would be, we had to know the slope to tell us how high up to go. And we could just find that value by taking y1, and then we want to add the change of the y value to that to get the next coordinate. So we got to add the change of the y to get to that. However, I never gave you the change of y. I instead gave you change of y over the change of x, the slope. So to simulate this change of y, I'm going to have to use what was given to me, which is plus the slope, but that's not dy, that's dy over dx. So I just need to multiply that by dx, or the delta x. And then they would cancel out the dx's, and you would be left with plus the y1 plus the change in the y. And what that would simulate is that y2 was here, here's y1 plus up y, the change in y to the next point is y2. So this is kind of the formula of Euler's method here. Let's say I wanted to get this point, the third y point here. Well, to get the third x coordinate here, it was just by taking wherever I was at x2 and then adding the change of x to get to the next point. And the change of x every time is a fixed amount. We can see we're just adding 1 every time. So this is a fixed value. We're keeping it a fixed value, adding a change of x of 1. The change in y, so for 3, we would take wherever we were at y2 at this point and then add up the change of the y. And the change of y changes, it's not fixed. Look at this length is smaller than this length. It goes up much steeper here. Again, to get the change in y, you can't just plug in plus change of y. I never gave you the change of y. Instead, I gave you the slope. And the slope is dy dx. But if you multiply that by the change of x, which again is the fixed value for our change of x, these would cancel out. And you would just be technically adding the change of y. So the dy dx is not a fixed value. Keep that in mind. Okay, I'm just going to kind of re-put this into my notes here, this idea. Okay, so what is this Euler's method? It's a numerical approach to slope fields. So it's just kind of like using the slopes to find where that line is going to go by just taking a point and finding its next point by looking at the slope. It approximates a solution, so very important to know it's an approximation, to a differential equation. That's a dy dx equation that just tells us slopes and that's it, with an initial condition. So if you have a slope and an initial condition, we can do this. And why would we use this? Because some differential equations cannot be solved easily. Some you cannot work backwards and find just the original y equation. It's just impossible to do. So how does this idea work? How do we find the next point as we move along? And notice as we move along, the exact solution is different than the approximation, but it's still an approximation. It gets close potentially. So how do we get to the next point? Here was the idea. You start with an initial given x value and a given y value. So let me just mark off some point right there. Let's say that's x1, and that would be y1. So you have some initial there. Then to get to the next point, we have to get to the next x value by taking the initial plus how much we decide we want to change, how much we want to change our x value. So it could be a change by adding 1, or it could be adding 2. Obviously, the smaller the increments here get, the more accurate it's going to be. But so let's call this the change of x. We'll actually move 2 boxes this time. And then up will be the change of the y values. And this will be x2. And then this point would be y2. So to get the y2 value, you have to start with y1, plus we have to go up from there a change of y. And change of y, as we've said before, is not given to us, but instead the dy dx can be given to us. So we have to put dy dx times the change of x. Then we just keep repeating this process. To get the next x value, to get x3, you would add x2 plus the change of x and going this way. Change of x. Then to get the next y value, you'd have to add up the change of the y. So you take y2, wherever we were at, and then add up the change of y, which we find by doing dy dx times the change of x. All right, just make a note that this dy dx is not fixed. This delta x is a fixed value. Fixed value.